There. Yay. All right, guys. So, any questions from? Have you guys tried any of the homework out or anything left over? Yes.
Can we do something similar to 14D?
Oh.
I guess that's really the only one that's similar to itself. But.
Yeah. Let's see. So A, B, C were okay?
Yeah.
Okay. So what happens when you try 14D? So here you've got, they give you the differential equation just so you can stare at it, but why is it 2 to the 4th plus 3? Now I like this. Now look. Do you see how that would imply its solution to a homogeneous? Do you guys see that? No, not yet. Okay, you will. That would imply it's a solution to a homogeneous. That would be my YC component. That's my YP component. And if you look at the equation they gave you, is it equal to 0? Is it homogeneous? Just a little side note. This has nothing to do with the question. Just a side note. No, it's equal to 24. So notice when you put a 3 in, you get 8 times y is 24. And then 3 prime and 3 double prime is 0. So that's your particular solution. So those make it 0, and that makes it 24. YC plus YP. Do you have to know any of that to do this wrong? No, but, you know, I'm a teacher. I try to do it. So what happens in part D? You guys take a minute. If you haven't tried this yet, try to figure out what C has to be for this to happen. What type of problem is this? Boundary value. I like it. BVP, not BVDs. I like that. Is that too old of a reference? Maybe my BVDs. Yes.
What number is it?
Y2 equals 15. Oh, this is 14D. I thought I wrote that. 14. My bad. I mean, really, the nice thing with this is you don't have to take any derivatives, right? So you should see something semi-quickly here. Anybody there yet? So when you plug a 3 in, you're supposed to get a 1 out. So this leads to this. When you plug a 1 in, you're supposed to get a 3 out. There you go. Yep. C1 plus C2 plus 3, right?
Yes. C1 0.
Oh, plus.
And then this one, you get 15 out when you throw a 2 in. So you get 4C1 plus 16C2 plus 3. And you know that C1 is negative C2. You can use good old substitution there. Or elimination, don't matter.
Okay.
When you try to plug that in, let's see, does something weird happen? So I know this to be true. I don't know if I want to do any more for you. I mean, that's almost done. Does something weird happen? Negative C2, you get 12 C2 equals 12. You get C2 is 1. C1 is negative 1. Something weird? Oh. I thought they might intend something weird, but I don't see anything weird happening. No? Yes? Anybody get the answer? Anybody hear me mumbling up here?
Negative 1 and 1.
Yeah. You plug that in, you get negative 4C2, so you get 12C2, subtract 3 is 12C2 is 1, and so C1's got to be negative 1. That looks nice and normal. Sometimes you guys, when they give you the DE, you sort of start doing derivatives, and if they don't say anything about verifying the solution, you don't have to do any of that. It all depends on if you need derivatives for this, and in this case, I didn't need any derivatives for this. Good old boundary value problem. Okay. Yes?
Can we go for 24? Or just like the setup for it?
Oh, okay. Now here's the thing. When they say Or when I say, verify that the given functions form a fundamental set of solutions for the DE. There's two things implied in there. To be a fundamental set of solutions, the most basic thing you need to be is you better be solutions. So you got to verify that they both actually work. And then the second thing, to be a fundamental set of solutions, all the candidates have to be what?
Separable.
Independent from each other. I like it. So you can set up Wronskian if you have to, or there's several problems where you don't have to do that. You can just see they're not independent, or you can see that they're not.
What'd you say it was called?
For which, I'm sorry, I just said a lot.
Yeah.
Wronskian, yes. I'm feeling like we might want to focus on doing a couple of matrix, just determinant problems by themselves. Is this a possibility? Just looking at determinant, just by itself, right? Okay. And I'll show you some shortcuts on some stuff. Okay, all right. I didn't really say much about that, but what was the question?
It's just a formula. I'm just not familiar with it.
Oh, okay.
That's
So
why I haven't seen it before.
let's look at this. It should sort of, even if it's hyperbolic cosine and sine, and you don't know that much about it, are cosine and sine independent from each other? What do you think?
No,
Why not?
because they're just phase shifts of each other.
But they're phase shifts, which is not a linear. Believe it or not, it's not a linear thing. You can't multiply one or something to make the other one happen. You have to internally phase shift it, which is not a linear operation.
Okay.
I like it. So they are just phase shifts from each other, but they are independent of each other. And you could do that with a little Wronskian. Let's do a little tiny Wronskian, little baby Wronskian. Let's just look at cosh and sinh. Does somebody remember what is it about cosh and sinh, the derivatives? Anybody remember that? I think if you forgot, they got it.
Cosh derivative, cosh is sinh, derivative, sinh is cosh.
Yeah, there's no negatives, right? I like it. No? You don't remember that?
Remember that?
Oh, that sucks. You guys never learned hyperbolic stuff at all?
No.
Okay.
I did, but it wasn't really focused. It's one of those we
Is
didn't
that
really
for the
focus too much on
agent
it.
of action?
All right, let me
Just so you know, this
let me
is
see if I can remember.
Exactly.
Yeah, the asymptote's at an angle. That's about all I remember from
Maybe I
it.
should know it.
And a box thing.
Let me see if I remember this.
Yeah.
It's been a while.
So I remember solving it.
It's a minus or plus. I always
All I
forget.
remember.
I remember that.
Don't ask me how to do the box. I just remember.
Something like this. Let me see. This is the one level down. This is like cosh and sinh are actually linear combinations of e to the x and e to the negative x that we just defined as cosh and sinh because they have properties that are similar to sine and cosine. And they're sort of related to what sine and cosine would look like if I use hyperbolas instead of circles, which is what I call hyperbolic. That's some weird shit. I don't know if that's right. To be honest, I never remember who's minus and who's plus in there. I don't know if it says in here. It's been too long.
Is that important for the hyperbolic?
Not really. I mean, you guys sound like you had never seen this shit before at all, so I at least wanted to show you where it comes from.
Well, I remember in the end of 280 we did that, where we broke down the functions into e's and stuff like that.
Okay.
Exponents.
Yeah, there's
That was all hyperbolic.
chapter 11, I think, is the hyperbolic. Is it chapter 11 from your old 280 book? And you're all like, sounds great to me.
You know us pretty well.
Like 30 years ago.
But real quick, watch. Let's see if Jeff's got this right. Sinh prime, right? The derivative of sinh would be the derivative of this side, right? Let me write it like this to make it really easy. Let's see if I got the minus and the plus in the right place. So what's the derivative here? What happens? I'll do this part.
Minus
Plus
plus
1/2
1/2
x.
Negative x. And so that's, I mean, it's really not going to show me, is it? Oh, well, I was hoping. One of them's plus and one of them's minus, but I can't remember, to be completely honest to you. But they're both linear combinations of e. I should know, but I'm not going to hurt myself. Oh.
I was going to think cosh is symmetric, so it should be the one that goes up.
Yes. So it should be, maybe these are backwards.
No, it should be, yeah, that should be right.
Okay. What matters is the hyperbolic sine and cosine are not defined similarly to sine and cosine, right? They're defined as linear combinations of these functions, and they have a lot of similarities to cosine and sine, which is why we call them what we do. You with me? So you never learned like sinh and cosh derivatives and stuff like that? Okay. Good to know.
If I saw I was looking up, it was right there.
Oh, man, that just sucks. Sorry.
Does it just simplify things? Is that the point of it?
Yeah, it just consolidates stuff. Yeah, and it's just the derivative rules become easier to remember if you consolidate this stuff. I mean, they're just very, very useful functions, really. Anyway, okay. So I'll shed a little tear for that, but you can always reference the front. If you haven't done this yet, you're kind of silly. It's hard for you to know, a lot of you guys reference the front here a little too often, but then again, you're like, well, when do I do it and when can't I? All right, I understand that. You really need to know how to do more derivatives or more integrals on your own without referencing a table. And whenever I have a test or something, I'll give you a form of an integral if you need it. Otherwise, I expect you to be able to do it somehow using some process. Okay, which hopefully you've learned. Where was I? All right. So, if I were to, now that we know these are equal to each other directly, there's no negatives in here. Okay. What would the Wronskian look? What's the Wronskian look like in general for? This is f of x, and this. I can't remember now how the book does it. Do they call it y1, y2? Y1, f1, f2. Good. So say that's f1, that's f2. So in general, it's f1, f2,
F prime,
f1 prime,
F2,
f2 prime. So this will be
F
cosh, sinh, cosh. Now, you would hope that there would be some similarity with trig identities, too. Because what do you get when you do this?
Cosh squared minus.
You get cosh squared.
Minus sin squared.
I like sinh. Oh, where do I put this? Cosh squared and sinh squared. So you can kind of break it down to those to see what this becomes.
1, 1,
It's going to be some kind of, you would think it's going to be some kind of constant, possibly, right? But if you do that, I'll let you guys finish the problem. If you throw that in, and you throw that in, and you square them, and you put them together, see what they come out to be. What am I looking for? For example, if I do the Wronskian and I get a constant, if I got 1, what does that mean?
They're linearly independent.
They're independent because when is this 0? Never. If I got x, they're independent as long as...
X is not 0.
Yeah, so if your interval does not include 0, then they're essentially independent for all you care, right? Or your interval has to change to allow for it to cut that part out. All right, cool. So that basically, if you get... What about this? We always forget that thing does. It's never 0, so it's linearly independent everywhere. Negative infinity unless there's some other part of your DE that makes the interval shrink. All right. So let's focus for a minute. Let's go past hyperbolic. Let's focus just on determinants. I did that one really quick, but 2 by 2 determinants are just A, B, C, D, right? Yeah. A, B, C, D, and they are just AD minus BC. AD minus BC. That's 2 by 2. So beautiful. Which is why the process for 3 by 3 is to make them 3 2 by 2s. And then it's easy. Now let's do a full determinant. Let's do one with just numbers in it. How's that sound? Is that all right at first?
Sure.
You're all in.
Yeah.
Wow. Beautiful, man. Concrete shit? No way. Haven't seen that in a long time. I think we did this though, didn't we? But I'll show you a little shortcut. Sort of. Let me make no zeros in this thing. Ha ha ha. All right. No zeros, so there's no better row than any other necessarily. So let me remind you how to do this. What you can always have sitting over here next to you is the little plus, minus, plus, minus, plus, minus, plus, minus, plus. That is not difficult to make. That's your little sign matrix that reminds you what sign the things have. Your little coefficients. What do I mean by that? So somebody pick a row or a column for me.
Right in the middle.
This one? I want somebody to go, pi! No, all right. No, all right. I didn't do that on purpose. So if I use that, it doesn't matter what you, in fact, if I wanted to, I don't want to waste the time, but if you picked any other row or column, you get the same number we do right now. It's just a recombination of all the same numbers. Okay, you're just going to get the same number at the end. All the math's the same, it doesn't matter. So this means that it's going to be negative 3 times, now what are all the parts that are not in 3's row or column? 2. 1's in 3's column. So 2, negative 1. 5, 1. Plus 1. Is everybody with me so far? I mean, that's, on one level, you can just accept this is a process. I'm not going to teach you the ideas behind this because that's not DE, sorry. But you can look this up. Plus 1, now what's not in here, it's going to be all these in the corners. Is that cool? Minus 4. What's not in this, guys, is going to be bam, bam. And now you got a bunch of little 2x2s that are easy. So I mean, negative 3 times 2 minus negative 5, so 7. Plus 1 minus 2 is negative 1. Minus 5, 9, 36, I think. Sure. So this is negative 58?
Yeah.
Negative 2. There you go, buddy. Now, let me show you a little shortcut. Let me see if I remember the shortcut. Jeez, I just realized it's been forever since I did this. If you basically redo the matrix a little shadow next to it. Yep. You do diagonals. It's easier when you have IJK if you've done that. IJK stuff, yeah. Because then I can always just, it doesn't matter. Let's see if I can remember. Is it bam, bam, bam?
Yes.
Yeah, so you just multiply those. Those are all positive. So let's see what we get. So the shortcut, sort of. To be honest, I really don't use the shortcut too much, to be honest. IJK I do because it's, I don't know, just nicer. So I get 1. See it? 1 times 1 times 1.
Yeah.
8 times negative 2 is negative 16. Negative 3 times 5, negative 15. And now I do minus.
There's one more.
Say again? What happened?
The one. The diagonal.
No, you don't need that.
No. No.
You only start with the first Wronskian or the first.
Yeah. Yeah, you actually, to be honest, you don't even have to write this. But, okay, I'll keep it there. You guys see? Bam, bam, bam. So very often we just do the first 2 columns. I love you guys. Let's just see if we get the same number. And then we get minus 2. Right? Negative 2 times negative 1 is 2. Minus 2, I'm going to minus all these. Minus 20. And then minus 6. What it's supposed to be? Maybe.
Yeah.
Let's see. Yes? Oh, thank God. So let's see. 8, 28. Yeah, I'm going to trust you. 38, 48, 59, 58. Yeah, negative 15. Yeah. And again, it's just this is just a little shortcut that just does the same math. And again, in a linear algebra class, maybe I'll spend a little more time on this, but I'm not going to. Or a pre-calc class where you're doing some more stuff with matrices. What's up, guys? Are you guys all right? You guys look concerned? Yes.
So the Wronskian is just to find the determinant, and that's just.
So the Wronskian is a specific is a determinant of a specific matrix, but it's just the determinant doesn't change. It's always this idea. For a 3 by 3. Yeah.
It's just to find that to check for dependence.
And this is specific use of determinants on a matrix that's set up with functions and derivatives to see if they are linearly independent. I love it. So determinant does not have anything to do with linear independence or not. It is a part of a process to check linear independence. Okay, yes.
Being linear independent of like certain terms means there's no combination of those two terms or those however many terms to create that other one.
Yeah, you can't take linear combinations of two to make the third one.
Okay.
Yeah. So a lot of the earlier homework problems you should be able to answer very quickly. There's one that's like, somebody just asked you 5 cosine squared and sine squared. How can you prove to me those are dependent very quickly? Can you combine combine multiples of 2 of them to create the other one?
Cosine
Yeah.
x plus sine x
It's
plus
square.
square.
No. Well, do you have a 4?
No.
No. But cosine squared plus sine squared is
1.
so 5 cosine squared plus 5 sine squared is 5. So yeah, 5 is a linear combination of those 2. So these are linearly dependent. I can make this one with those 2. So that's like stupid extra information. So if I said, guess our age, I'm twice as old as him, and he's half as old as me. I'm like, thanks. I don't know what this shit. Right? I just told you the same stupid thing twice. So this is 3 pieces of information, but not really. This is already known. Screw it. So if I needed 3 functions, I haven't found the third one yet. I have 2, but not the third one. Now, if you want to see that these are linearly independent, then you could do a Wronskian, or you could just say there's no way to... No. Now, if you only have 2, one must equal a constant multiple of the other one. That's the only way it would work. If you have 3 or more, then you can kind of juggle different ones. You can leave some out. This one, is this equal to some constant multiple of this? Oh, hell no. They are related by identities that involve funky-ass manipulations of things that aren't up here, but no. Okay, I like it. Okay. Is that enough for the moment about that?
Are we going to need to use determinants? Or
Yes.
just
If I ask you that problem, if I just say verify these are linearly independent, and
So it's just the Wronskian.
you can't see them, like, I don't remember the homework problems, like that was number 17, the one we just did. It looks like,
24, 27.
let me see. Put your arm down. There you go. 29, it's hard to argue necessarily. It's kind of hard to argue that they are independent because you can't go through every possible combination and say, see, I didn't get one yet. I didn't get one. Right? So if they are independent, you almost have to use the Wronskian in a sense. If they're x squared, x cubed, you certainly can argue that. Those are like, they don't have anything to do with each other in any way. You can kind of argue it, but the quickest way to judge is Wronskian it, especially with polynomial shit. But on the test, I'm going to say use a Wronskian to show that blah, blah, blah. So I could either say just show that these are linearly independent, or I can say show that these are form a fundamental set of solutions. And what does that really imply then? The Wronskian helps show they're linearly independent, but you have to show that they work. You have to show that they're solutions, yeah. I like it. How are we doing so far? Is that... Okay, I like it. Does it make sense that I can't just, if I have a third order homogeneous linear, I have to have 3 distinct things that's attached to C1, C2, C3. They can't have one that's a combination of the 2 because then I don't really have 3. Okay, I like it. Okay, anything else from homework? Good, okay, let's get back into... You have to get that excited, Jeff. I know.
So Professor, the reason that we need 3 different functions is because it's a 4th order.
Third order.
Okay. So we
Yes.
need as many functions, independent functions, as the order of the differential.
And we did hit a theorem finally that confirmed that. I think I told you that earlier. I can't remember if we hit a theorem that actually said that. All right, you guys are all like, maybe. Okay. But it's related to like the fundamental theorem of algebra, the same idea. That's the same, not the same proof or anything, but the same feel to it. I'm pretty sure we did. I'm pretty sure there was, but I'm not going to look for it right now. So just a couple things to finish up in 4.1. I think we left off pretty much at fundamental set of solutions. Is that true or not? I mean, you seem to understand when I said that phrase. No?
Fundamental set of solutions.
Yes, fundamental set of solutions. So let's start there then. So I know we definitely did linear independence, obviously, but that leads up to the idea of the fundamental. Maybe this is the one that says. No, I don't think so. Yeah, this one says it, but not so. This is at the bottom. No, it's not. Where are you? Here we go. Middle, page 125. If you have it, so basically what it says, this is theorem 413. If I have an nth order linear homogeneous DE. All right, now I want you to realize a few things. We're going to do this several times. We're going to kind of like investigate a new form. We're going to start with a lot of assumptions, and then we're going to kind of let go of some of them and see what happens. So here, this is like if you have a beautiful, unbelievable, awesome DE. Basically, is what all this says. It's linear. It's homogeneous. Holy shit! I mean, it's beautiful. Really, there's nothing really too freaky about it. If it's nth order, and you have a set of y1, y2, up to yn